Alright, welcome back everyone to the continuation of the DB2 lecture series. First things first, I've been asked to step up my background game, and I think what you see in the back is a move in the right direction. I would hope so. Alright, so let's get back into business. And the business currently is the discussion of the heap files, the primary storage that PostgreSQL uses to store the rows of our relational tables. Heap files are named heap files for a very good reason. It's just an unordered heap of rows. And that gives heap files quite some freedom of how to organize themselves internally, and how to deal with deletions, for example. Deletions could leave holes in such a heap file. Holes in quotes here, because that is meant to represent the empty space that may be created once we use the SQL delete command to remove data from a relational table. Such holes, such space on pages could be reused. And heap files indeed have a particular internal data structure, the free space maps, that help to organize this free space, to reuse it efficiently, and to help using the 8 kilobyte pages in an efficient manner. Okay, so let's talk about these free space maps, the FSMs, in the next few minutes in this particular course. Free space maps are maintained for each heap file and record the number of bytes that are still available, that are free in a sense, on each of these 8 kilobyte pages or blocks, as we have called them. The free space map is a kind of add-on service for each heap file that is able to respond to two particular free space map operations. So given a row of n bytes, a new row that I want to place in my heap file, which page P would have enough space, sufficient space to hold these n bytes of my new row? And in particular, let's look for a page P in my heap file that is in the vicinity of some other page, say P prime. And why would I be interested in the vicinity in particular? Because, as I've told you, packing data in adjacent pages in physical vicinity has some advantages when I later use my heap file operations to read data back from the disk. Physical vicinity means less seek operations, less rotational delay, more efficient block access when I'm talking to my SSD and my HDDs. So, hey, free space map, please give me free space on some page that is in vicinity of a given page. That's one operation. And the other operations, of course, is, hey, I've removed some bytes from a particular page P. Hey, FSM, please update yourself so that this free space is reflected and can be reused later on when I want to place new rows inside my heap file. Okay. There's one particularly simple, but I think quite clever implementation of this free space map inside PostgreSQL, and it's actually organized as a kind of tree. The leaves of this tree, these are the leaves of this particular tree, they represent the individual pages in my heap file. So this sample tree would represent 8 pages, the 8 pages numbered 0 to 7 in my heap file. And the leaf nodes of this tree-shaped FSM structure would represent the free space that is still available on these particular pages. So the free space on page 6 would be recorded with 4. This is not 4 bytes, but in PostgreSQL, the 4 stands for 4 times 32 free bytes that are available on page 6. 5 times 32 bytes are available on page 7. Please see this footnote here on this particular slide. Why do we record such free space in units of 32 bytes? Because this means that the free space on an 8 kilobyte page divided by 32 byte units can be represented by a single byte. So a maximum value of 255 here in this place in the leaf nodes of the FSM would represent an entirely free page in my heap file. Okay, so that's just for compactness reasons. Single bytes suffice to represent the free bytes on an 8 kilobyte page here in these leaf nodes. The inner nodes represent the maximum of free space that is available in the subtree below these inner nodes. So representing these two pages with a maximum of one 32 byte unit of free space leads to an entry of 1 in this inner node. The entry of 8 in this inner node means in this subtree, which represents the pages 0 to 3, there is a maximum space to be found of 8 times 32 bytes somewhere. It's here on page 3, but somewhere in this particular part of the file, there is one page that could hold 8 times 32 bytes. And if this is sufficient to hold a new row, that would be a candidate subtree to search for a particular page in. That's how we read these FSM trees. The root node with its entry 8 here represents the entire file and says, hey, if you want to place information inside the heap file, I'm representing the largest contiguous free space that you will find in this heap file on the pages of this heap file is 8 times 32 bytes. Okay, so that's how we read these particular tree-shaped FSM trees. Okay. How would the operations implemented on these FSM trees? So to find a page that has at least 4 available slots, that is 4 times 32 bytes of free space, in the vicinity of, say, page 4, so that would be our entry point here, we would have to search the tree upwards until we find an inner node that indicates that, hey, there is more than, say, 4 available slots in the vicinity. So our search would start here at page 4. We want to find free space in the vicinity of page 4. Page 4 only has 2 free bytes available. Okay, so we move along that edge, that dot marked edge here, to find the 3 in the inner node here. That means in the vicinity that is represented by the subtree, the maximum free space would be 3, not sufficient to hold 4 times 32 bytes. Okay, so let's move further up. Okay, that looks better. Okay, so somewhere in the subtree represented by this inner node, there is free space available of 5 units of 5 times 32 bytes. That's sufficient. So let's search down the tree again. We came from here. We know it's 3 here. Let's search down the tree. Okay, that subtree will hold 5. 4 is sufficient. So let's dive down in this particular subtree. Page 6. Page 6 would be the target page to hold a new piece of information that occupies 4 times 32 bytes. Okay, that would be operation 1. Find me a new page with sufficient space in the vicinity. The other operation, like update the FSM to reflect that in this case, in our example, more space is available now. So how would that work? So let's in this state of the FSM, page 4 had 2 available units of free space. After the update, because we have deleted stuff, for example, we have now 4 available units on page 4. Okay, so let's update the FSM tree to reflect that. We walk up the tree across this dotted edge again to find that this node has to be updated. You see it had 3 available units of space in this subtree. It's now 4 available units in this subtree. Okay, so we update 3 to 4 and then walk walk towards the root of the tree, walk further upwards the tree along this dotted edge to find 5 here. 5 means the subtree has a maximum free space of 5. I can only contribute 4, so that won't override the 5. The maximum 5 would stay at this particular place. 5 is still the correct free space for this particular subtree. The update can stop here. We don't have to walk the tree further upwards towards the root. Only the bold nodes here, these 2 nodes, are affected by the update, and we only have to walk 2 edges. That's the basic idea behind this free space map in PostgreSQL. Okay. So let's try to see how this actually works in practice in PostgreSQL. So let's switch back to editor and shell here. There we go. So let's see. Here we go. Okay. So there's a particular extension in PostgreSQL that allows us to have a peek at these FSMs, at these free space maps. If we want to use that in a particular database that we are running, we have to enable that particular extension inside the database. So let's do that. Let's create the extension pg_free space map in our database. Let's do that. Okay, so extension created. I already had that extension created, but it might not be the case in your database. So just use the create extension command to enable peeking inside the FSMs. So let's have a playground table to work with. We will recreate the unary table that we were working with earlier, and we will place 1000 rows in this table. 1000 rows will occupy 5 pages, I think. Okay, so let's do that. Table created, everything fine. This is our playground. Okay, so to look at the FSM files and to see what we can find in there, how large the FSM files are, how large the actual heap file for table unary is, and so on, let's again visit the data directory of PostgreSQL. So let's recall where the data directory resides. This is the directory. Let me switch to a shell here. All right. Copy the path. All right. And so enter the data directory. Okay, very nice. So now for the subdirectories that hold the database, in this case, I'm working on the Scratch database in my PostgreSQL system. Let's locate the subdirectory for the Scratch database. Okay. We have done that before. Okay, 16386. And let's look up the heap file that will hold the unary table. Let's do that. 73021. Okay, so back to the shell. So we will go to subdirectory base, and 16386 is the subdirectory for the heap files of the Scratch database. Okay, and then the unary heap file, the heap file associated with unary, is called 73021. I'm appending asterisk here to see that, okay, there's not only the heap file 73021 of size 40 kilobytes, which is expected, 5 pages times 8 kilobyte. That's the 40 kilobytes allocated by this or allocated for this heap file. That's fine. But there's also a free space map that has been allocated alongside the heap file, and it's this file in which the tree-shaped data structure that we were looking at the slides is stored. Okay, so we have located our files there. That's perfect. Okay. So now let's query the free space map data structure inside PostgreSQL, and that's where the PG free space map extension comes into place. We will get this particular table valued function from this extension, and you can see I'm passing the table name here. this will allow me to peek inside the leaf nodes, the leaf nodes of the FSM tree for table unary. Okay, this command will update the FSM. So let's make sure that the FSM is really up to date. When we are looking at it with the pg_freespace function, we will really find the current state of things reflected in there. So let's run these two commands. Okay, so this is the leaf level of the free space map tree for the unary table. It has 5 entries because there are 5 pages in this file. That's expected. And this is actually the available space measured in bytes. So no space left on the 4 first pages, no space left, but plenty of space left, about half a block left on page 4. That would be the current free space situation in table unary. Okay, so let's see how things progress if we now start to create holes inside the heap file. For example, by deleting this particular range of rows between 400 and 500. The A values in column in column A of my unary table, they range from 1 to 1000. So in the middle of that file, we will now delete 100 rows. Let's do that. 101 rows, of course. Okay, so 101 rows gone. Okay, so how's the free space situation now in table unary? So update the free space map and query its leaf level. Okay, so now there's some free space in the middle of the file. Some space has been freed on page 1, some space has been freed on page 2, so there is no holes in the middle of the file, while there are also some fully occupied pages, and there's of course still free space in the last page. Okay, so some free spaces here. How is this being used by the heap file? The heap file could take advantage of the fact that rows may appear in any order. So new rows might just be placed inside the holes. There's no row ordering involved. There's no insertion order or something to respect it. New rows could be placed in any hole. Let's see if that actually happens. And we will do that by inserting a new row, a new value, a new row into our unary table. I'm using a row that carries value -1 here as a sentinel value that can be easily detected, easily spotted between the positive values between 1 and 1000. This sentinel should be easily spottable when we are inserting it into the unary file. Let's see where it will be placed. Okay, insert this particular row, the sentinel. Okay, then update the free space map and query its state again. Okay, looks similar, but not quite. Look at this value, 1664 of 3 bytes on page 1. So 1664, how does this compare to the situation before? 1696 on page 1. So yeah, so 1696 is 32 bytes larger than 1364. The freely available space has been reduced by exactly 32 bytes. That's no surprise because the free space map operates in a granularity of 32 bytes. So one further 32 byte units of space has been occupied by the new row that we've been inserting into the unary table. And you can see the new insertion has hit page 1 somewhere in the middle of the file. It has not been appended at the end of the file or something. Okay, so now if we look at the contents of table unary, the sentinel value should be somewhere in the file, probably somewhere in the middle of the file, somewhere on page 1. Well, let's do that. So these are all the values. I will scroll by. It's 900 rows because we deleted stuff from the middle of the file. So let's look. I'm scrolling. So let's see. Oh, there's a sentinel. There's a sentinel somewhere in the middle. There's this hole that was left by the deletion of rows between 400 and 500. And here, somewhere on page 1, the new sentinel has been placed. Let's check whether the -1 really has been placed on page 1. So how can we do that? All right, we can just look at the row IDs. We can look at the row IDs that are associated with these rows, and the sentinel value should actually be assigned. Let's look at all the row IDs. Should have been assigned a row ID, a RID, whose first component should be 1. Okay, so let's look at this. Okay, so the final rows of that table, they are residing on page 4. The final 96 rows. Okay, page 4, but we are looking for the sentinel -1, scroll. Okay, somewhere we must be close already. Okay, yeah. So the -1 has been placed on page 1 in the slot number 174. We will talk about these slot numbers in the future, but yeah, that's right. The new value has been placed somewhere in the middle of the file. Heap files have taken advantage of the fact that rows may be inserted at any place, no insertion order, whatever is to be respected. Holes are being filled with the help of the free space map data structure. Okay. So looking at this, now that we've deleted 100 rows and only inserted one more row, if we really have a compact representation of the heap file for the unary data table, I don't think that we need 5 pages still. Maybe 4 pages would suffice. And we can ask the database system to really aggressively compactify, if there's such a word, the heap file, to render it fully compact, to rewrite in the most compact fashion. And we can do that by requesting a full vacuum on the unary table. That will take some time and take some effort. Normally in a database system, you would only do this during whatever offline hours, during midnight. You would request full vacuums of the heap files of your tables to really rewrite them in a very compact fashion. So let's do that now. It's a small table, it should go reasonably fast, and then query the state of the free space map for the unary table. All right, so a full vacuum has been run. It has found 900 non-removable rows. Okay, we knew that. They were originally stored on 5 pages. And now that the full vacuum has done its job, 4 pages. 4 pages suffice now. 4 pages which are really fully packed with rows are now, 4 pages are now sufficient to store the contents of our file. So let's see whether the file system really, first let me check that, let me check the heap file in which the rows for the table unary are now residing. Let me check the heap file, because we will see that a full vacuum really rewrites a new file. All the rows are placed inside a new file. This is the ID, the name of the new heap file, 73024. Yeah, okay, so a new heap file has been constructed. This is the size of the new heap file. Let's see. So the new file has this many bytes, and one page can carry 8 kilobytes of stuff. Yes, okay, 4 pages in the newly fully vacuumed file. We have saved space. Very nice. Okay, so much for our brief discussion of heap files free space management, and a caveat that there is no defined row order in relational tables. Heap files make good use of holes and free space, can compact themselves with the help of FSM trees. Okay, so much for now. See you soon. Bye bye.